Have you ever wondered how we connect the dots in a world that's just full of gaps? Well, today we're diving into a really powerful mathematical idea that does exactly that. It's called interpolation, and it's kind of like a secret weapon for understanding the world. So I want you to think of yourself as a detective for a minute. You've got clues, right? A few data points, some scattered moments in time, but the full story? That's missing. The real action, the truth, it almost always lies in the spaces between what we actually know. So how do we crack the case? For example, imagine an animator who's making a character jump. They'll probably draw the starting pose and, the final landing pose. But to make that jump look smooth and realistic, they need to figure out all the frames in between.
Or hey, what about a weather forecaster? They might get a temperature reading at 8 in the morning and another one at noon. But what if you want to know the temperature at 10 a.m.? They have to make a really good guess about what happened in the middle.
And it's the same thing in finance. A stock's price gets recorded when the market closes each day. But analysts, they need to model its behavior and understand its potential value at any given moment during the day. You see the pattern here? All of these are the exact same fundamental problem. And the tool that we use to solve all of these mysteries is called interpolation. It's basically the formal process of making a highly educated guess about that missing data. It's about filling in the gaps based on the clues you already have. Now, it's really important we don't mix this up with its cousin, extrapolation. Think of it this way. Interpolation is about finding values inside the range of what you already know. You're reading between the lines. Extrapolation, on the other hand, is trying to predict what happens outside that range. It's like trying to predict the future. Today, we're sticking to the case at hand. We are all about interpolation. So how do we actually do it? Well, our first method is the one that probably feels the most natural. It's called the LAGRANGE method, and it's all about, you guessed it, directly connecting the clues we have. The simplest version of this starts with a really basic idea. If you have 2 points, what's the most logical path between them? Well, it's just a straight line, right? This is called linear interpolation, and it's surprisingly powerful. And the process is pretty straightforward. You just take your 2 known points, you apply this clever little formula that calculates a weighted average, and boom, that gives you any point along the line connecting them. Let's see it in action. Okay, here's our case file. We've got 2 data points. We know that when x is 2, y is 1, and when x is 3, y is 5. So the big question is, what's the value of y right in the middle when x is 2.5? Now, what's really cool here is the logic behind this Lagrange formula. You don't even need to get bogged down in the math to understand it. It's basically just a balancing act. The idea is, if our target x of 2.5 is closer to one of the known points, that point gets more say in the final answer. In our case, since 2.5 is exactly halfway between 2 and 3, both points are going to have equal influence. Makes sense, right? And the answer is 3. Exactly halfway between 1 and 5. I mean, it's just so clean. This shows you how that simple straight-line assumption can give us a perfectly logical answer. But let's be honest, the world is rarely simple enough for just straight lines. Life is full of curves. So what happens when we need to model something a little more complex? Well, that brings us to quadratic interpolation. So what happens when that path between our clues isn't a straight line at all? Think about the arc of a thrown ball or the dip and rise of a stock price. A simple straight line is just a terrible fit for that. We need a better tool for the job. So if 2 points give us a line, what do 3 points give us? A curve, specifically a parabola. This is the heart of quadratic interpolation, and it lets us capture all those bends and arcs in our data, which makes for a much more realistic model. Okay, I know, the formula looks a lot more intimidating. But here's the secret. The idea behind it is exactly the same as before. It's still just a weighted average. Each of our 3 points gets its own little term, its own chance to pull the final curve towards itself. It's the same beautiful pattern, just scaled up for a more complex problem. All right, let's switch gears completely. The Lagrange method is all about connecting a series of separate clues. But what if we took a totally different approach? What if we used a different kind of tool? Let's talk about something called the Taylor series. This is the mind-bending question behind the Taylor series. Imagine you don't have a bunch of scattered points. Instead, you have deep, incredibly detailed knowledge about one single point in time. Could you reconstruct the entire path just from that one moment?
The Taylor series builds the entire path piece by piece, using everything it knows about that one spot. Think about a rocket launch. First, you know its starting position on the launch pad. That's your first term. Then, you add its initial direction, its velocity. That gives you a straight line guess of where it's going. But a rocket doesn't just go in a straight line, right? So you add the next piece, its initial acceleration, which describes how that velocity is changing. This bends your straight line into a curve, a much better prediction. And the Taylor series can just keep adding more and more terms, like the rate of change of the acceleration, and each one refines the path even further, building this incredibly accurate picture from just that single, well-understood moment. So what we have are two powerful but very different detective tools. We've got the LAGRANGE method for connecting scattered clues, and the Taylor series for building a whole path from one deep clue. Now, let's talk about why choosing the right one is so important.
So when do you use which tool? Well, LAGRANGE is your go-to when you just have a set of distinct measurements, like temperature readings or data from a science experiment. But the Taylor series? Oh, that's an absolute powerhouse when you know the underlying physics of a system at one specific moment, like all the forces acting on that rocket at the moment of launch. And believe me, this isn't just some abstract theory. This math is running silently in the background of our lives, all the time. It's what makes the animation in video games look so smooth, it's what scales up a digital photo on your phone without it looking all blocky, and it helps create the incredibly complex models used for weather forecasting and scientific research. It's everywhere.
So interpolation gives us this incredible power to fill in the missing pieces of the puzzle, to create a complete picture from just a little bit of information. But that also leaves us with a really fascinating question. You see, the line or the curve that we choose to draw, that's an interpretation. It's a choice. So with this power to connect the dots, what story will we choose to tell?